This program is brought to you by Stanford University. Please visit us at stanford.edu.
I just want to go very briefly over the two-slit experiment again. I don't think we ever quite finished, so let me finish that discussion. The two-slit experiment, and we made a very simple version of the two-slit experiment. There's a source. I called it an electron. It could be a photon. It could be any kind of particle, whatever. But let's call it an electron since I'm used to it. The electron is emitted from the source. Now, if you like, you can imagine that the electron can be emitted from any one of several places. There is a barrier to the electron over here with some openings. Again, the openings could be in any one of several places, but for simplicity, let's just suppose that there are only two openings. I don't remember what I called them last time. I think I might have called them +1 and -1. I hate that. That doesn't sound good. So let's call them A and B this time. A and B. I think I called this point 0, and the rest. The electron can go through the little hole at A, it can go through the little hole at B, and just imagine that the rest is blocked off so that if an electron hits any one of the other sites, for simplicity, you can just pretend that it gets reflected back. If it arrives at A, it can go through the slit and arrive somewhere at the final end over here. And I think I labeled those points by integers. So this could be the mth site over here. The 0th site would be over here. M equals 1, 2, 3, -1, -2, -3, and so forth. And we'll start an electron over here. So initially, we haven't discussed very much how states change, and we're going to do that. Not tonight, I don't think, but eventually we will. But the most important thing is that states change in a linear way. That means if you start with a linear superposition of two states with coefficients, what it evolves into is the same linear superposition of whatever any one of them evolved into. So if, for example, well, let's start. We start with an electron in state 0. Incidentally, for the present purposes, the electron has no spin. We don't have to worry about the electron spin. That's irrelevant for the moment. It just is at a place. And so the states of the electron are simply characterized by which one of these vertical positions they're at. Right? So we start the electron right at the center at point 0. It evolves, and it evolves into a linear superposition of states at A and B. The electron has no particular preferred reason to go to either A or B, and let's suppose it's nice and symmetric. So it has equal amplitude to get to A or B. So 0 goes to A plus B. Now, what does A plus B mean? It means a state in which the electron could be at A. You could find it with a probability of half at A, and you could find it with a probability of half at B. And it's just a quantum superposition of the two configurations. Now, when it gets to A, if it gets to A, it then moves on, and it moves on to the screen here. So we can say that A evolves into some superposition, arbitrary superposition, nothing special, a sum on n of some coefficients which represent the probability amplitudes, psi sub m, of the electron now being at the mth place. That's what happens if you were to have started. The way you can think about it is forget the whole B altogether, start an electron at A, and wait a while, and it will arrive at a superposition of states with different amplitudes, psi sub m, m. Or if you started at B, it will also evolve, and I think I called the coefficient here phi m times m. Okay, so let's first begin with one hole completely closed. The electron can only go through A. If it can't go through B altogether, we can forget this. We close it up. And the probability that the electron arrives at the mth site here is just going to be psi star m psi m. And I'm focused on the mth site. Don't worry about any of the others. Just the amplitude that the electron gets to point m is psi m, and the probability that it gets there we can just call Pm is psi star m psi m. That's assuming it goes through the root A. In other words, if we have blocked off hole B. Maybe we should give it a name. Maybe I should stick an A over here to indicate that it went through the opening A. Likewise, if I close up the hole A and open up the hole B, then the probability is phi star m phi m. Now, in classical logic, classical statistics, classical probability theory, statistical mechanics, if you had a beam of particles which was not made with enough precision, so with some uncertainty in it, some of the particles might go through A, some of them may go through B, but our expectation would be that the probability to get to M would be the sum of the probabilities of going through A or going through B. We would just add those probabilities. Not so in quantum mechanics. In quantum mechanics, what we have to write is that if we start at A, we get to here. If we start at B, we get to here. But if we start at A plus B, if we start with the state A plus B, which the electron is sort of equally between these two, then what we have to get to A plus B will go to summation of n, psi sub n times n, psi sub n times m, I guess, sum on m, plus phi sub m times m, and I can just represent that by adding psi to phi, so it just becomes sum of psi m plus phi m times m. All right, let's forget for the moment the sum. Let's just focus on a particular point, m. Not even interested in the sum here. Just focus on a particular point, m. What is the probability that the electron gets to m? And the answer is the square of this amplitude, or the square, it times its complex conjugate. And so the answer is Pm, the probability to get to m, when both A and B are both open, is psi, well, let's just square that out, which will give 4 terms, psi star m psi m plus phi star m phi m plus psi star m phi m plus psi m phi star m. All right, so the answer is the sum of the two original probabilities plus an extra term, and the extra term is called the interference term. The interference between the two trajectories, one of them going through the upper hole and one of them going through the lower hole. This is no analog in any kind of classical statistics, this extra term. And to see how weird it is, I mean, for example, if m happened to lie right on the symmetry point here, then you'd expect psi and phi to be equal by symmetry, and this would give you 4 times the probability of going through either hole. It's not hard to arrange by going off center here. You can find, well, you can either go off center or you can do other little tricks in the beam of particles here to make psi equal to minus phi, and then you would just get 0 probability. So despite the fact that the electron can get to m through A or through B, if you open A and B in that particular circumstance, the electron just won't get there. As I said, that's as weird as anything I know in quantum mechanics, and it's very, very simple. But now comes the question, which we started to talk about last time. Well, I think we may have even finished it, but I want to review it again. What happens if somebody actually is present and actually watches whether the electron goes through one hole or the other, and even records whether it goes through one hole or the other? Then what happens? Surely then you must know whether the electron went through A or B. So we made up a little system. We added another element here. We added a spin. The spin can either be up or down. It could be the electron's spin itself. There's no reason why it couldn't be the electron spin, but I simply wanted to think of it as an external measuring apparatus that could record the presence of the electron, so I didn't want to think of it as part of the electron. Let's not think of it as part of the electron. We add another degree of freedom over here, which is a spin which can be up or down. Up or down. And let's not ask exactly how it happens, but when the electron passes through the hole A, there's no spin at B. When the electron passes through the hole at A, whatever it does is it gives a kick to the spin and it flips it. That's an assumption. An assumption about the way the spin is located, how it interacts with the electron. We measure over and over again that when the electron does pass by the spin, it does kick it over. So we know what happens. An electron passing by the spin kicks it over. It kicks it from, let's say, from down to up. All right, now let's reanalyze the experiment. We don't just have an electron. We have an electron and another spin. So we have to add something into the state vector here. We can't just describe it as an electron at point 0, but we have to describe it as an electron at point 0 with the spin down, or our apparatus unactivated. We can think of it as the apparatus being unactivated. And so that's our initial state. If the electron goes through the upper hole, then it becomes state A. The electron is at point A, but the spin gets flipped up. If it goes through hole B, the spin doesn't see the electron, and it stays pointing down. So now we have something new. The two states A and B are correlated and entangled with a spin. They're entangled with a spin such that by measuring the spin, you can tell whether the electron went through the upper hole or the lower hole. All right. Well, what happens to A up? Once the electron departs from here, it no longer interacts with the spin, assume, and so I assume that it will not kick the spin over again, and so all that will happen is A will evolve exactly as A evolved before, except the spin will remain up.
This is not a measurement, though.
This is a measurement.
Are we collapsing a wave packet?
Mm-hmm. Collapsing the wave packet simply means destroying the interference pattern.
No, I mean at A and B, when you're changing the spin, possibly. You're flipping a spin.
Yes. That constitutes a measurement of the electron. And it constitutes a collapse of the wave packet of the electron. When thought of as the composite system of electron and spin, no, it doesn't collapse the wave packet. The only way to collapse the wave packet of a combined system is for something else to look at it. Forget collapsing the wave packet.
It's only two things in there. If you had collapsed the wave packet, you wouldn't have AU plus BD. You would all have one or the other.
No.
You forced it into
No. Collapsing the wave packet is a language to use if you don't want to remember that there's this other spin there. Then you forget the other spin, and you just say the wave packet got collapsed to either A or B by the presence of the spin, But if you keep the spin present, in other words, if you include the apparatus into the description, then you don't talk about collapse of the wave packet, you talk about establishment of entanglement.
Okay, and the apparatus in this case is simply the spin.
It's just simply the spin. It could be anything. It could be a pointer that has two states. It could be the emission of a photon, so that down could stand for no photon, and up could stand for a photon being present. So it could be anything which distinguishes which of the two holes it went through.
And it's different. I mean, even if you didn't have the spin, you bet it go through the top or the bottom. It interacted with this metal aperture that had the two holes.
Yeah.
I mean, there was some
Well,
momentum.
the question is whether it left a mark on the metal. Okay. Now, the answer is yes. It could leave a mark, but that depends on details of this metal plate that's there, and in particular, if the metal plate has an energy gap, if it takes some energy to excite it, and the electron is low energy, it may not have enough energy to excite anything interesting in this system here, and so it will not leave a mark. Right, but that's the criteria, that it doesn't leave a mark.
Okay, let me say this. I was sort of saying, well, it's going through, and it has some momentum to get to M as opposed to way up high. But, and maybe we're not. We have to discuss, but you don't have a spread. So you have a spread of momentum states in A and B, but it's the same.
Okay.
There's no difference.
Wait. Well, are you asking whether? Are you asking whether you can tell which hole the electron went through by looking at the recoil?
Yes.
Okay, good. Let's take that care. Good. The electron goes through the upper hole, and obviously it gives a little kick upward to the. If it goes through the lower hole, it gives a little kick downward. All right? So it changes the momentum of the screen here. All right, now, we're getting a little bit ahead of ourselves into a little more complex situation, obviously, but let me tell you what the answer is. The answer is that the screen here itself has an uncertainty in its momentum because it's localized in space. Through the uncertainty principle, which we haven't talked about, the screen here, or whatever we call it, the barrier is well localized. Because it's well localized, it has a spread in its momentum. So it looks like this. Now, that's the momentum space distribution. That's the probability distribution for the momentum. And it's pretty well spread. And the reason it's pretty well spread is because the location is very, very nicely definite. Right? So it's pretty well spread. Then the electron goes through the upper hole. If it goes through the upper hole, it gives a little kick, and it shifts this distribution a little bit. If it went through the lower hole, it was shifted the other way a little bit. But you can't tell uniquely, and in fact, as long as the kick is small by comparison with the spread in the momentum space wave function here, you basically, it almost completely overlaps with it. And you don't get kicked into an orthogonal state of the motion. Okay, so that's a very, very good question, but there is a very, very good answer.
Yeah, so like last week, there can be a case where you're not purely in up or down.
Yeah. Right. So that's right. It's exactly the same thing as if instead of saying when the electron goes through here, it kicks down to up, instead it kicks it to almost down plus a little bit of up, or the other way, whatever. And that will allow you to have different degrees of destruction of the interference pattern. But I want to take the extreme example now, where you do a complete measurement, where you do an absolute measurement, which means that you establish a complete correlation between A and B on the one hand and up and down on the other hand, so that by looking at the spin, you can determine completely and uniquely which of the two holes the electron went through. That's the notion, if you like, of a experiment, of a measurement, establishing an entanglement between a system and an apparatus. The apparatus just being the spin. Okay, so let's just do the dot all the I's and cross all the T's. And now in this situation, let's see, B, we never finished here. B did not kick the electron up, so B, if the electron goes through B, the spin stays down, and it just continues to stay down. So now we have a state, as I said, with this entanglement between the wave function of the electron psi or phi on the one hand and up and down on the other hand. All right, let's just go through the very formal motions of calculating the probability that the electron is found at point M. Right? So there are two ways that the electron could be found at M. It could be found with the electron at M with the spin up, or electron at M with the spin down. So what we have to do is build the projection operator onto the state where the electron is at point M. All right, remember what the rule is. If you have some property that you want to represent by a projection operator, you take the subspace corresponding to that property, you find a basis of orthogonal states in that subspace, and then you build the projection operator as a sum of dyads, sum over all the basis vectors in the subspace of the dyad composed out of them. All right, what are the states in which the electron is at M? Well, there are two states. There's M up, and there's M down, M down. That's it. Those are the only two states in which the electron is found at M. So this is the projection operator onto the configuration where the electron is at M. So now what we have to do is we have to take the final state. What is the final state? The final state is the sum of these two. We add these together. Now we cannot factor out M up and M down and write it in this form here, because each one multiplies a different ket vector. Psi m multiplies one ket vector, phi m multiplies another ket vector. All right, let's just do it. Let's bite the bullet and do the whole thing. M up, I need more room. M up plus M down, M down. That's the projection operator. Let's put something around it. Now we take the state vector. The state vector is sum on n. Oh dear. That's a summation index there. Sum on n up, psi n plus phi n down. Likewise, on this side over here, we have the same thing, psi star n, psi star n up plus phi star n down. Put some brackets around all these things. All right, now, first of all, there are the non-cross terms, the non-interference terms, the terms like psi star psi. Let's just look at them. Psi n here, this piece here has an up spin, and it can only combine with the up spin over here. It's orthogonal to the down spin, and so the inner product of an up with a down is 0. You only get a contribution from up with up, and furthermore, you only get a contribution when n is equal to m. The inner product of up n is only non-zero with m up when n is equal to n, when m is equal to n, and then the inner product is 1. Okay, so out of here, you pick out the single term where m is equal to n. Likewise, from this side, m has to equal n, and up has to equal up, otherwise you don't get a contribution. So from the direct terms, you get psi star m psi m. Okay? And also, similarly, phi star m phi m. Okay? That one comes from this term in the projection operator. But you get nothing from the cross term, because the cross term coming when you try to combine a down with an up. Up here can only go with up here, but then the up over here will kill the down over here. So the projection operator does not allow you to combine a psi with a phi because the spins are orthogonal in the various terms. All right, so here's the result. The result is that if you do a measurement, the result is the sums of the probabilities, exactly as you would have imagined in classical physics. So if you don't look at the route that the electron takes, and if nothing looks, not just you, but if no mark is left that you can ever, or anybody else can ever determine afterwards whether the electron went up or down, or through the upper route or the lower route, then there's an interference pattern. Yeah. Probably. Where? Here? No. Above this, probably. Probably. Yeah, where is it? Over here? Yeah. 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 But the main point is you've got to match not just, whoops. Sorry. I think he's the one who's sorry. You've got to match not only the ends, but the uppy-downiness of the state vectors, and that will cancel or kill or destroy the interference patterns between psis and phis.
So can you say at the bottom that's just the sum of two single-slit experiments on top of each other?
That's right. It's exactly the same as if it was classical statistics. Yeah. Yeah.
If you repeat that again, if no mark is left, or whether it goes to A or B,
then there's an interference pattern. In other words, that means that you have to add amplitudes. If there's, yes.
So if you kick the electron also at B, then you will get.
What's that? Oh, you get exactly, if you put the spin B.
If you kick the electron at both A and B, then you will get.
Kick the electron, kick the spin.
Yeah.
Yeah, good. Okay, let's suppose the spin is located in some symmetrical situation, let's say over here, where it gets equally kicked, whether it goes through A or B. Then when it'll come out, let's see, where will it come out? Over here. Then we'll just have A up plus, let's see, up, yeah, A up plus B up, right? And then it'll be exactly as if, then there will be an interference pattern. In the end, you will not be able to tell from the fact that the spin is up which hole it went through. So good. Then that would leave us in this situation, right?
The way you're telling which hole it went through is finally you measure the spin of the electron at the end, right?
Well, I don't have to do any. I do not have to measure the spin of the electron. The electron has measured. The electron has done the measurement. The electron has done the measurement, not of the electron spin. The electron has done the measurement of which hole it went through. I don't have to look at the electron. I don't have to look at the spin to know that the interference pattern will be destroyed. I don't actually have to look at the electron. Just the fact that the information is recorded by a system, I could look at it, but just the fact that it's recorded, and it's recorded in the orthogonality of up and down, that's enough to destroy the interference pattern. So I don't ever have to look at the electron. I just look at the electron. Sorry, I keep saying electron. I don't ever have to look at the spin. I just look at the electrons coming through. I have a beam of electrons coming through. I do this over and over again. I send through an electron, do the experiment. Electron arrives somewheres. And then I put the spin back in its original position, do the whole experiment again. Put the spin back in its original position, do the whole experiment again, and gather statistics of what the probability is that the electron arrives in different places. I never actually have to look at the spin. All I have to do is look at the electron and see where it came out, and I will discover that there was no interference pattern. Yeah.
If the screen has sufficiently little mass that it recoils, then that will also destroy the interference?
Yeah, that's right. basically, if the momentum wave function of the screen here is narrow enough so that when the electron goes through, it gives it a kick and kicks it to a configuration which is orthogonal to the original configuration, then it will destroy the interference pattern. Right. In fact, there's another way that interference patterns get destroyed. If the electron, now this is subtle, this is very subtle, but if the electron goes through the upper hole here, then it may, and it's a slow electron, let's say it's a very slow electron, not too fast, it will emit some radiation. Every time an electron is accelerated, and it has to be accelerated to go from here to here, it will emit a photon. Right? So, or it may emit a photon. It may emit a photon, not that it will emit a photon, it may emit a photon. If it goes through the lower hole, it also may emit a photon. The probability of emitting a photon, incidentally, by electron is very low. It's about 1 part in 100 for a low-energy electron. So only 1 part in 100 does it emit an electron. So it does leave a little bit of information in the radiation field. But with only emitting a photon 1 part in 100, you cannot be certain when you look at the system and discover there was no photon emitted, you cannot be certain which hole it went through. But on the other hand, if you really whip the electron through there fast, in other words, a high-energy electron, and you really arranged it so that the electron went through one hole way up on top and the other hole way on down on bottom, so that it really had to whip around and accelerate a lot, then the likelihood of emitting a photon would be larger and the interference pattern would be more destroyed. So just the ability to emit photons is enough to partially destroy interference patterns, and it does. Yeah.
So when you actually do the experiment, you have to perform a statistically large number of measurements
absolutely.
In order to build up the data set,
Yes.
from which, in fact, you infer the probability distribution.
Yes.
Because you can,
Absolutely.
your ability to approximate the probability distribution is a function of how many experiments
Right.
electrons you have.
Right.
So what you're saying is that in the case of an electron with a low probability of emitting a photon, which in principle could be detected, that is one source of noise in
Yeah.
practical experiment.
Yeah. One source of interference, one source of destruction of the interference pattern. You can call it noise if you like.
Well, what you see practically is the experiment, from a theory point of view, says those detector statistics will contain dark and light areas. Areas of the detector where you get particles and areas where you don't get any particles. But in fact, if you can get 1001 contrast, you did really good. And there's going to be some residual number of particles that show up anyway in the so-called dark or forbidden areas. So my question is this. If you have a large number of these things, and you have a system that maybe reads this, what you're saying is that if there is any possibility of determining after the fact which hole the electron went through, that will destroy the interference?
Yes. Yes, but you may also have a partial situation where you, by looking at something, you may be able to say it was more probable that you went through the upper hole than the lower hole. Yeah, that's easy to do. For example, as I said, when the electron passes through here, instead of kicking down to up, it just kicks the direction of spin a little bit, so that it's mostly still down and just a little bit up. That will destroy the interference pattern a little bit. It'll blur it a little bit. Yeah. Right. Yeah.
Would you say that the 1 in 100 times that the photon does get given off is the one time when that element of the interference pattern? That would be one of the cases where.
Well, yeah. What you could do is you could collect statistics only for those events in which a photon was emitted. Okay? And then you would find the interference pattern worse. Now, it's not quite completely clear because if a photon is emitted from here, it may not be completely orthogonal from a photon emitted from here. The wave function of the photons may not completely be orthogonal, so you can still have a little bit of blurry situation there. But you know, I mean, you can destroy interference in many, many ways. Just the atmosphere, and this is the biggest source of interference destruction. In particular, why don't you see me as fuzzy? Why do you? Well, I assume you don't see me as fuzzy. I mean, I start out here, and you don't. You close your eyes. Close your eyes. Everybody, close your eyes. Okay. And now open them. You'll find me in the same place. You don't find my wave function having spread out all over the place. In fact, you could wait forever and ever and ever, and you would not see my. Or the moon's wave packet doesn't spread. Part of the reason is that the moon is heavy, but the other reason is that it's constantly bombarded by atmosphere, by other things, and so it's as if it's continuously measured. And every time it's measured, if you continuously keep measuring a thing, it will not spread at all.
Can I make a side suggestion here on your course next, whenever you teach it?
Yeah.
I'm using terms like collapsing wave packet. You're talking about measuring. You just gave us a theory of measurement. That's something that would be good to teach in a course.
I'm teaching.
Well, well, you're saying that things are always interacting with one another, so.
Well, I'm trying to give you an extremely precise example. All right, I give you an extremely precise example, and now we can extrapolate from that. We could work out some other examples. We could work out some other examples in which partial experiments are done. I think those are straightforward, but I'm trying to give you a crystal clear example where there's no ambiguity, so that you can see the mechanism by which the interference pattern is destroyed.
And entanglement forces you to do that. I mean, you know, 30, 40, 50 years ago, you could sort of get away with loosely not worrying about it too much. But,
yeah, well, I mean, even, you know.
I mean, except for the final consequence.
Question.
But collapse of the wave packet, and collapse of the wave packet here means collapse of this wave packet, which literally means that you throw away the off-diagonal terms, the mixed terms, the phi psi terms. That is, you can describe it that way. You say, I did a measurement, I collapsed the wave packet. But you also ought to be able to describe the composite system of the electron and the detector in a way that doesn't involve any hanky-panky with collapsing wave packets and so forth. The corresponding correct description of a composite system is entanglement took place. So that's what that's the importance of entanglement in doing measurements, and obviously it's a very important part of nature.
Question. I don't know if this is relevant or not. If it is not relevant, just ignore it. But you said that photon will get emitted because the path is curved. Just in the theoretical case, if there was a gravitational field present, so that it's actually a straight line in the gravitational field, how would that change the situation?
Wait, say it again? No, let's see.
Like, the path from 0 to A to M is curved.
Yeah.
So for that reason...
Well, I mean, there is no well-defined path, but you can more or less see that the electron had to accelerate to go around the corner here.
Right.
So.
Now, if there was a mass sitting between A and B...
Oh, if there's a mass sitting between
so
A and
that it's actually a natural path.
Yeah.
Would it change the situation?
Or you could just have one of the slits not be a deflection at all.
Wouldn't change it. Yep, you could have one of the slits not be deflected, but then the other one would be. Good. Look, we can think of 1,000 million variations on this theme. The end of the story is, if anything tags leaves a mark telling you which way the electron went, that destroys the interference pattern. It'll destroy it partially if it gives you some probabilistic information about which way the electron went. Not certain information, but biased toward one direction or the other.
I have a question.
Yes.
Does this definition of interference contradict anything we learned in continuum electromagnetics? Multiple photons interacting with each other in geometries and so forth. Is it the same thing? Is it another way to look at the same thing, or is it radically different?
The interference pattern here, when there are many, many electrons, or let's say many photons to make it simpler, when there are many, many photons coming through all at once, the interference pattern is nothing but the interference pattern of wave motion, of electromagnetic waves. The fact that it also happens for electrons tells you that there's some sort of wave associated with the electron. It's not the electromagnetic waves, it's the electron wave function. Okay, let's move, one more.
I just had a question about I missed last class, so the parameters of the beam are that it has an equal chance of being emitted with a momentum that would put it between A and B?
Well, Oh, which would put it between A and B?
Well,
Yeah.
the setup is that it's either fired at A or B. Is that setup of the beam?
Well, we're just assuming that if it arrives anywhere in between, it just bounces off, that this region is closed off. Yeah.
So,
Yeah, it's blocked off. Yeah.
Well, the short answer is cat then. The cat really isn't a superposition of alive and dead unless you have some kind of external measurement.
No, the cat is not in a superposition of alive and dead. Okay? The cat is not in a superposition of alive and dead. That's exactly what is not true. What is true is the cat is entangled with another system. What is it entangled with? The question of whether the bullet was fired or not. So it's a composite system. Let's say it consists of a gun and cat. So it's a composite system, gun and cat. And the gun can be in two states. The two states are unfired and fired. Okay? The cat can be in two states, dead or alive. Okay? You start with a live cat and an unfired gun, U for unfired. And then something happens and you wait a while, and after a while the system evolves into live cat with some coefficient alpha, live cat, unfired gun, plus some other coefficient, dead cat, fired gun. Okay? It is not in a superposition live plus dead. It's in an entangled state with the gun. All right? So you cannot do any kind of interference experiment between live and dead. If you were to calculate the probability of live and dead, you would have no cross terms. It's the gun itself, the firing of the gun has left a mark, or firing or not firing. The point is you don't have to look at the cat to find out if it's alive or dead. You can look at the gun. So that tells you it was entangled, and it is it's basically exactly the same mathematics as this. So no, the cat in Schrodinger's experiment is not in a superposition of alive and dead. The composite system is in a superposition of live, unfired, and dead fired. Good. One more.
I think you're being very careful to talk about destruction of the interference pattern as being something different from a measurement, which is what goes on at the final.
No, I'm saying when a measurement takes place, it destroys the interference pattern.
Okay.
Yeah.
Well, exactly. But my question is really, what goes on at the final screen that lets us talk about probabilities rather than states?
Let's say it again.
What happens why at the final screen can we reduce this all to probabilities rather than having to go carrying the entangled states forward?
Well, look, there is a probability postulate in quantum mechanics, and you construct the projection operator and take its expectation value, and that's the probability. I don't know what to say beyond that.
What happens is you get the interference pattern or you don't.
Yeah.
And that's
Well, Okay, I set up some experiment here, and now, why am I, can I talk about the probability of the electron on the screen and not at the middle?
Say it again?
Why do I talk about the probability of the electron being at the screen and
Okay.
some position,
Okay.
and not talking about it going through A or B?
You can talk about it, well, you don't want to talk about it at A or B unless you measure it. If you measure it, you can then go and ask this spin, did it go through here or didn't it go through here? And you will have a probability for it having gone through here or having gone through here. Now, what about at this end? At this end, at some point you have to do a measurement as to where the electron was. In other words, the electron has to do something at this end to record the fact that it has arrived at one of these positions. We haven't talked about that. I just said it either arrives at one of these positions or it doesn't. But if it arrives at one of these positions, another kind of measurement can happen. The other kind of measurement would be the blackening of or it could be, we could, for example, put a spin at every one of these sites. If the electron arrives at that point, it flips this spin up. If it arrives at this point, it flips this spin up. In other words, at the end of the day, I am imagining that we do some experiment over here to find out where the electron arrives. I've sort of suppressed that part of the experiment.
It's sort of the same thing as just putting more barriers in between. Like if you had a scintillation screen that will give off a photon and then the electron continues on, you would then have it ricochet in some unknown direction. And you would again have a situation where...
Sure, but I mean, to complete the experiment, you actually have to measure where the electron is. Measuring where the electron is means that some sort of mark is left on the system by where the electron arrives over here. It could be because there are spins aligned along here, or it could just be because when electrons arrive on photographic plates, they blacken the spot on the plate. And we look at the black spot. We don't actually look at the electron, we look at the black spot. But the black spot becomes entangled with the position of the electron along here.
I think the answer is that you're using a position projection operator.
Yes.
That is itself effectively a measurement.
Yes.
At the point N.
Yes. But the process of separating a system into that which is measured and that which measures is always ambiguous. You can always say, all right, look, the experiment really doesn't happen until I look at the spin. In that case, you would add another element where you could either just say this combined wave function here collapses, or you could add another ingredient in, me. And me also has two states. Me having seen spin up and having recorded it in my brain, and me having seen spin down and recording that in my brain. So we could say, once I look at this, it evolves into something even more complicated. A up and me having seen up, plus B down and me having seen down. But then you could be watching me. Okay? The point is, there's a degree of consistency. There's a degree of consistency that the probability to find either A or B with up and down is the same as the probability of A up, me seeing up, B down, me seeing down. So at some point, there's no point in going further and entangling anybody else in the experiment. But if you did, you would still have consistency.
In the case, in the Schrodinger's cat case, it's more than the gun that's entangled with the cat. There's smoke in the box. So
There's smoke in the box also, but then Schrodinger is on the outside of the box, and he's not entangled. But then he looks in, and he sees one or the other, and so Schrodinger himself becomes entangled with the box, the gun, and the cat. And the process, and then Wigner, who's waiting outside, he's going to ask Schrodinger, what did you see? He becomes entangled. No, the whole world is a highly entangled thing.
because they're all correlated with each other.
But they're correlated in a consistent way. Yeah. Yeah, there's no interference. There's no interference if, unless there's been nothing to record which thing happened. Yeah. One more. We want to move on.
Doesn't the uncertainty principle figure into this now? The process of measuring affecting the event being measured?
Absolutely. Well, one particular instance of it is as was pointed out, you might worry that the recoil of this screen here might ruin your measurement by leaving a mark as to whether you went through the upper hole or the lower hole. It's the uncertainty principle and the uncertainty of the momentum of the screen here, which doesn't allow you to determine unambiguously which hole the electron went through. So certainly, uncertainty principle plays a role here. Yeah. The most important thing well, not the most important thing necessarily, but what you should keep in your mind is that the difference between a classical experiment and a quantum mechanical experiment. A classical experiment, you always imagine that a classical experiment can be done in a gentle enough way that you can find out what you want to find out without disturbing the system, okay? Without disturbing the state of the system. Here, you can see that we have definitely disturbed the state of the system. The measurement is not done until the entanglement has been established. And establishing an entanglement is a significant change in the state of a system, and a measurement is not done until that entanglement is established. Once that entanglement is established, it changes the answers. It changes the answers whether, for example, there is or there isn't an interference pattern. So classical physics, you always imagine that you could make your experiment gently enough that it doesn't influence in any way the system that you're studying, or perhaps in an arbitrarily small amount of change in the system. Whereas quantum mechanically, you are forced to, in order to do an experiment, to establish an entanglement, and that's a big change. That's a significant change in the system. Yeah.
What about the distance between A and B? And let's say it gets arbitrarily large. What effect does that have on the interference pattern?
Well, that depends on your assumptions. Nothing particular, I don't think. I don't think it does anything particular. Yeah. Of course, what it will do is it will make the probability of going through either of the holes very small. So both the psi's and the phi's will be very, very small if you take the holes to be very far away. The overwhelming probability will be that it hits the wall and gets bounced back. Chances of it getting out to very far distances may be very much smaller. So it might, but apart from that, I don't think it has any special effect. Yeah.
It seems really lucky that all this superposition is linear.
Mm-hmm. Well, I don't know if it's lucky, but.
Is that really fundamentally true, or is that?
Yes, it's fundamentally true. No. Well, that's another question, but we've talked about this over and over again, and I keep telling you I don't know the answer, except I know from experience how hard it is to modify things a little bit. So I'm not going to answer that question because I honestly don't know the answer. It's an empirical fact, and it's the basis of quantum mechanics, but it's not easy to make a logically coherent story out of a slight bit of nonlinearity. It becomes a mess. Now, really it's the replacement of one kind of logic by another. It's the replacement of the logic of classical sets by the logic of subspaces. Why the Lord in his infinite wisdom decided on subspaces instead of something else, maybe the Reverend Haggard knows, but I don't. Excuse me. What?
You might consider for the moment the possibility of particle proceeding past the target to the detector.
The target being this.
Correct.
Yeah.
Such that we would perhaps be able to determine the trajectory, which slit it passed through after the event, whether there was interference or not. Does that change the results we get?
Well, I think what we could do is we could put another set of detectors over here and ask about interference over here. Is that the sort of thing you're?
So I was at first considering, would there be some way to put a detector in A based on some effect that would happen later in time, such that, but there's really not a way to do that. And then it occurred to me that, is there a way perhaps after the target where we'll be checking
Which way the electron went through?
such that we would determine
Well, all I can say is if there is something left in the system that allows you to determine, but typically no. I mean, if it got past here without leaving any mark on the system, when it gets here, offhand, not really, no. But if there is a way to detect which way it went through, that will destroy the interference pattern.
even if that detection event would happen after the
Yeah.
interference event.
Yeah. As I said, you don't even have to do the detection as long as the detection is implicitly.
I mean, the order of time is not significant, right?
Well, you mustn't violate causality. Cause must precede effect. So other than that,
Yeah, but our measurement would, obviously a slit would have been chosen before the impact of the target, but if we were able to, based on monitoring it after it hit that point, determine which way it went through.
I guess we would have to set up a very specific experimental situation and analyze it, because I can't analyze in the abstract without having a very, very definite, concrete example in front of me. Well, the bubble chamber on the other side wouldn't tell you which hole it went through on this side. It would not. Not in general, no. I mean, say it again?
Let's say immediately following your barrier at A and B,
Yeah.
you have some magical, ball chamber.
Well, yeah, then you get a trajectory.
Oh, you mean if the trajectory remembers which way the electron went through? If you have a bubble chamber over here.
Well, let's say
No, right
just
after.
immediately following the.
Between A.
Over here?
Yeah.
Sure.
Where? A big bubble chamber, little bubble chamber?
I would say it covers the whole thing. That's
Okay, so big bubble chamber.
Yeah, sure.
Yeah. Okay, then what?
Well, does it, that would it presumably destroy the interference?
Oh, absolutely. 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 Certainly, for sure. Yeah.
Yeah,
Definitely.
there's automatically no
Yeah.
interference as soon as it reaches the bubble chamber.
Well,
Then it's constantly giving you.
just to be precise about it, we could put a thin wall of bubble chamber here. And then afterwards, the electron arrives over here, and we look over here and we see, do we see a track over here or do we see a track over here? The answer is that anything that leaves a track will certainly destroy the interference pattern, for sure.
But you got it on the opposite side of the target from what I was saying. So I guess maybe the real answer is just interference with the target with presumably keeping the.
Well, as I said, each example has to be analyzed separately, but the rule is very general. If there is a mark left on the system from which you can deduce the degree of ambiguity will determine the magnitude of the effect, but let's say which you can deduce unambiguously which of the holes the electron went through, then there will be no interference pattern. And that's the most general way of saying it. Now you can think of all sorts of examples, but always trace it back to that. Ask whether there is or there isn't anything left on the system which remembers. And always bring it back to this here.
When you get out of the situation where you have.
I'm trying to figure out how to get out of this situation. Why?
Things are already entangled with each other.
Yeah.
Okay, so at some point, you are able to perform the experiment where you do get interference. What is it that causes you to have that that degree of uncertainty to the frame, or whatever it is? Is it just
uncertainty, for example, in the momentum of this screen here? That's what you're talking about. Previous history.
Suppose I wanted to get an interference pattern after running it through the bubble chain.
Oh.
Now, at some point, I have a definite track. Now, what does the apparatus have to introduce in order to get an interference pattern later on?
Well,
Where did it come from in the first place?
Where did what
If
come
everything is entangled already.
That's not. No, it better not be entangled already. You have to start with some systems which are disentangled. Let's move on. Let's move on, and we can because I understand why it's difficult to move on. There's a zillion infinite number of questions, but I think it's a good idea, having learned the rule, go back and do the exercises yourself. See if you can figure out yourself the answer to some of these questions, because they're good questions. It's not they're not good questions, but I think we can go on and on and on forever and ever.
I still have the question.
What's that?
Where does disentanglement come from? Because obviously, pretty soon everything's going to be entangled.
By making a measurement. By making a measurement, you actually do some disentanglement. For example, by making a measurement of the electron over here, for all practical purposes, you start over again, and you start over again with the electron definitely over here. That electron is now, from your perspective, you throw away the other possibility. Having seen the electron, having seen the spin up, you simply forget this one here. You forget it altogether, and you say, aha, the electron is over here. Let's start over again. And now you can say, this electron is over here, and what you start with is the state A up. A up is not an entangled state. Okay, you just throw this one away. You say, I made a measurement, I looked at it, I saw that that the spin was up, so I know that the initial starting point was A up, and I throw away the other. Yeah, that's right. That's right. So we could. That's right. So we could make the experiment more complicated. We could put another pair of slits over here, and start with the electron starting at this point, and the spin would play no special role anymore. It was simply the thing that told you that the electron started over here. Well, something told you the electron started over here, and so it really was, in some sense, entangled with the electron gun or whatever it was that started the electron moving. So it's sort of a nested hierarchy of different levels of discussing the problem. As I said, the division, here's your system, here's your detector, here's somebody looking at it, here's somebody looking at it, and so forth and so on and so on. And where you draw the line between the system and the detection is ambiguous, but depending on where you draw the line, at some point you will have to say the wave function collapses. Right? But in observing this entire system here, you won't say that the electron wave function collapses. You will say the combination of wave function of electron, detector, and Schrodinger, or whoever, is collapsed by Wigner making a experiment on, this was a cat, I guess, cat, gun, and Schrodinger. You get the idea. And the only question is whether it's consistent. Whether it's consistent, whether at the end of the day, when Schrodinger comes to Wigner and says, what did you see me think? And Wigner says, I thought I saw you think that the cat was dead. And Schrodinger says, yes, that's what I saw, the cat was dead. That's consistent. And the quantum mechanics is hooked up in such a way that you don't run into inconsistencies in this manner. Let's move on. Let's move on. Let's move on. Let's move on. We've talked about entanglement. Well, we want to take a break. We have not gone as far as I had imagined we would, but that's fine. No, that's not a problem. Well, let's keep going a little. Entropy. I want to discuss entropy. Really what I want to discuss is how do you define a measure of the degree of entanglement between two systems? If I have two electrons and both their spins are up, they're not entangled. You learn nothing about one by looking at the other. There's no sense of looking at one and finding out some piece of information you didn't know about the other. So that's not an entangled state. Two spins both up. Generally, unentangled states are called product states, and in product states, each of the subsystems by itself has a very well-defined state that you might as well disregard the other one altogether. But they can get entangled. They can get entangled, and the amount of entanglement is a quantitative measure of it. There are many quantitative measures of entanglement, but the one we're going to talk about, and the usual one, is called entanglement entropy. So I want to explain what entanglement entropy is. It is the thing, if you want to find out whether some description of a composite system involves entanglement, the test is to calculate the entanglement entropy. All right, so first of all, let's talk about classical entropy. What is classical entropy? Imagine we have some system, and the system has some collection of states, classical. Now we're doing classical. So logic is Boolean algebra. It's just a classical set theory. There's the space of all possible states of some system, and let's take the states to be discrete. So there's some finite number of states. Let's call the number of states capital N. Now, entropy is not just a property of a system. It's a property of a system together with your state of knowledge about the system. In other words, it's something that has to do with both you and your state of knowledge on the one hand and the system itself. The less you know about a system, the more its entropy. The more you know about it, the less its entropy, according to the definition of entropy that we're going to talk about. All right, so let's see, how can we quantify that? All right, so there's capital N states, and let's suppose that what we know is that the system is in one of little n states. One of little n states. Capital N is not going to play any tremendous role for the moment. All we know is that the system is in one of little n states with equal probability for all those little n states. Then we would say we're ignorant, and our degree of ignorance is little n. Little n, it could be in any of little n states. The bigger little n is, the less we know about the system, right? If we knew that if little n was just 1, in other words, that would be the situation where we know exactly what the state of the system is, and it's in one of the states, one known state of the system, then we would say little n is 1. In that case, we would say the entropy is 0. We have no ignorance. We know everything there is to know about the system, and so there is no ignorance. What if little n is big N? If little n is big N, it means we know nothing about which state the system is in. That corresponds to the maximum entropy. All right, so let me give you one definition of the entropy, which is good for this situation here. It is simply by definition logarithm. It's called S, and it's the logarithm of the number of states that your ignorance allows, shall I say. Little n is, all you know is that it's in one of little n states, then the entropy is simply logarithm of little n. You're probably wondering why you take the logarithm. Anybody know why you take the logarithm? Yeah. Yeah. You multiply numbers of states, you add entropy. That's one way of saying it. Another way of saying it, let me give you another example. Supposing my system is again a system of spins. And I know something about a whole bunch of them, ups and downs and ups and downs and so forth. And I know nothing whatever about the system. I know nothing whatever about the system. How many possible states are there? Well, the answer is 2 to the number, now another completely different n, 2 to the number of spins. How many spins are there? Let's call them m spins. 2 to the m is the total number of states. And what's the logarithm of 2 to, and if I knew nothing at all about the system, then in here would just be 2 to the m, any one of 2 to the m's states. The logarithm of the number of states would just be proportional to m. So what the logarithm measures is the number of bits of information, a bit being a spin, right? The number of bits, now a bit basically means a two-level system. The number of bits is the number of bits, but the number of bits gets exponentiated to determine the number of states, and it's just a useful definition to go back to the logarithm, which is basically a measure of the number of little bits of information, a number of yes-no, or the number of up-down decisions that is contained in your degree of ignorance. Okay, so in any case, that's a definition. S is equal to the logarithm of n. Now, what happens if you have a more general situation? Instead of having, incidentally, in this case here, the probability, let's write down some of the probability. The probability, let's call these states I. All right, let's say the probability for I, the probability for the ith configuration is 1 over little n if I is in the subset n. This is the subset n. I've used it to label both the number of elements and also the subset itself. P sub I is just 1 over little n if I is in n and P sub I is 0 if I is not equal. How do you write that like that? Is not equal, is not in n. That's what it means to say we know the system is in n, but we don't know anything else. All right, now what do we have a more interesting probability distribution or a more complex probability distribution? Instead of having all of the probabilities be 0 or all equal if they're not 0, we can imagine a more general situation where we just have a probability P of I, period. It might be big in some regions of the face of the configuration space. It might be small in other regions. It might approximately be such that, that there's some subset here which all have equal probability, 0 on the outside. May or may not be. Just some P of I. I would like some kind of measure of the number of states that is included in this probability distribution. And I would like it to be such that it counts the state only a little bit if it's improbable and counts it a great deal if it's probable. I'm going to give you now a definition of the entropy, and I'll show you how it works, which is true for a general probability distribution. For a general probability, and I'll show you why you use this in a moment, but let's just define it first. The entropy for a general probability distribution is minus the sum over all the states of the probability of the ith state times the logarithm of the probability of the ith state. Okay. Let's see how it works. Let's see how it works. First of all, do you know why it's minus?
Yeah, those are all to be negative logs.
Yeah. Probability is always less than 1. So the logarithm of something that's less than 1 is negative. So this is really a positive quantity. This is really a positive quantity. Log of P sub I is always negative. Let's do an example. Let's calculate this. Let's go back to the first example here. In the first example, the probability was 0 if you're not in n, and 1 over n, 1 over little n if you are in n. So let's calculate then S. S is the sum over all places. So let's concentrate on a point inside n here. All right. What's the probability? It's 1 over little n. Okay. What's the log of the probability? Logarithm of 1 over n. There's a minus sign. And that's the contribution for any one of the states in here, right? For any one of them. What about the states on the outside? The states on the outside give 0 because their probabilities are 0. All right? 0 times logarithm of 0 is 0. Right? Logarithm is infinite for when p is 0, but p log p is 0. So you get for every configuration in here, you get 1 over n log 1 over n. Now what's the log of 1 over n? It's minus the log of n, so we can get rid of this and make it just log of n. But this is just a contribution from one of the points in here. How many points are there in here? N. So we have to multiply this by n, which is just equal to log n. So in the case where we have a probability distribution which is 0 or 1, it reproduces the original definition here of just logarithm of n. Right? What about the situation where there is only one point which has a non-zero probability, all the others being 0? In other words, when you know with certainty exactly where the system is in the phase space, in that case, only one of the p sub i's is not equal to 0. Okay? All the other p sub i's are equal to 0. Okay, so let's go to that one point which is not equal to 0. Let's just label it j now. Minus, or p, let's call it p sub 0. P sub 0 log p sub 0. Distribution is spread out over about n states. If it makes sense to say that it's spread out over n states, then it's just logarithm of n. Otherwise, a more general definition which captures the two examples that I gave, and that's really all it's intended to capture, is summation over I, p sub I log p sub I. That's definition of the entropy. Okay? As I said, the bigger the entropy is, the less you know about the system. What's the maximum entropy that this system can have? Why 1? 1? Logarithm of capital N. Logarithm of capital N would be the situation where you know nothing about anything, and so each one of the states has probability 1 over big N. You know nothing, and so it's just logarithm of capital N.
We don't know number of states, capital N, so we know that.
Yeah, that's all you know. You don't know which of those states is it. That's right. You don't know which of those states it's yeah. You know what the system is, but you don't know in which of the states of the system it is. That's what maximizes the entropy. Incidentally, the difference between maximum entropy and actual entropy is called information. If the entropy were exactly 0, you would have a lot of information. You have a lot of states, and you know which one it's in. So the difference between maximum entropy and entropy is the amount of information available to you, or it's defined that way. Okay. So in some sense, information and entropy are opposite sides of the same coin. Entropy is the information which is unavailable to you because either you're too stupid, too lazy, or whatever it is that, whatever reason, or the object is too small to see, or you're, whatever the reason. Okay, that is, now what does entropy have to do with entanglement? That will come, that will come. It is a measure of the degree of entanglement. Before we get on that, we need a definition, one mathematical definition. And the mathematical, I'm going to give the mathematical definition, then we're going to take a break because I'm getting tired. We'll take a break, and then we're going to come back and talk about the density matrix a little bit. I don't think we'll actually get to entanglement entropy tonight, but I want to set up the basic ingredients that go into it. A basic mathematical operation done on matrices. And since matrices are linear operators, you can think of it as a operation on operators. You have some linear operator. Let's just call it M. M stands for matrix, but can also stand for abstract operator. And let's suppose we have a basis. A basis. Oh, I'm going to assume well, no, I won't assume. No assumption. Let's take a basis of vectors in the space of states, whatever that space of states is. Let's call them I. And take the II matrix, the diagonal matrix element of M. If M is a matrix, then this just stands for the II diagonal matrix element. Here's the 1, 1 element, the 2, 2 element, the 3, 3 element, and add them all together. That's called the trace. That's called the trace of M. Now, you might think that this depends awfully much on which choice of basis vectors you choose. There are many choices of basis vectors in a space. You could choose, if it was three-dimensional space, you could rotate your axes and so forth. I'm not going to prove this. This is something, this is an exercise you can either do yourself. It's easy, or you can look it up in your favorite linear algebra book. The trace of a matrix is independent of the choice of basis vectors. It's an invariant. It's a quantity which does not depend on your choice of basis vectors. And so all choices of basis vectors give the same value for the trace. That's an important little theorem, and it plays an important role in what follows, but you look it up or prove it yourself. It's not hard to prove. Okay, that's the definition of the trace of M. We're going to use that over and over. But supposing the matrix in some basis happens to be diagonal, since it doesn't matter what basis we compute it in, we can look for a basis in which the matrix is diagonal. If M is a Hermitian operator, there will always be a basis in which it's diagonal. If M is not Hermitian, there may not be. But if there is a basis where M is diagonal, then the diagonal elements are nothing but the eigenvalues of the matrix. Remember, when a matrix is expressed in diagonal form, if it can be expressed in diagonal form, the entries are the eigenvalues of the matrix.
Excuse me,
Yeah.
question. Matrix in diagonal form means the matrix is inverse. Those two statements.
It may not have an inverse because it may not have an inverse. If any of the entries are 0, it won't have an inverse. Yeah. Yeah. But as long as the entries are not 0, it will have an inverse. Right. Okay. Good. No, actually what it means is that it's a function of a Hermitian operator is what it means. But if it's diagonal, it's characterized by its eigenvalues. And then the trace is nothing but the sum of the eigenvalues. That's a way of describing the trace which doesn't depend on the choice of a basis. The eigenvalues don't depend on the choice of basis. It's just if you happen to use the right basis, then the matrix will consist of a diagonal, where the diagonal entries will be the eigenvalues. But the concept of an eigenvalue transcends any particular basis. So if you know all of the eigenvalues, you add them up, and that's the trace of a matrix. The sum of the eigenvalues, in particular of a Hermitian matrix. In particular, a Hermitian matrix which always has a complete set of eigenvectors and eigenvalues. The sum of the eigenvalues is the trace. And as I said, it plays an important role. Let's take a break now for 6 or 7 minutes. Let's move on. Let me tell you what the role of a trace is, how it, let's go back for a minute to the classical situation. The classical probability distribution, some P of I. Let me just remind you that if you have a P of I and you have some observable, classical observable now, a classical observable just means some function of the points in the configuration space. All right? Some function which takes on different values for different states. So we can call it f of I. An observable is just a function of the configurations, just takes on different values. When you observe it, you find out something about which point you're at. The average of f, given a probability distribution P sub I, is of course the sum over I of P sub I, f sub I. You just weight the different values of f with the appropriate probability. Remember that probabilities all add up to 1. And this is the classical average or expectation value of f. I'll just call it f. I'll call it average of f. That's the definition of average of f. You could also call it the expectation value, although it's not necessarily expected. The trace, first of all, let me tell you, the trace is the analog of the sum over configurations. It replaces in quantum mechanics summing over all the possibilities. So trace becomes, or sum over configurations becomes trace. Sum. You'll see how it works as we go along. Now, there is a very similar formula to this in quantum mechanics, which of course involves a trace. And involves a trace of the observable times something. And that something is called a density matrix. And I'm going to explain it to you now in a very simple situation first. Supposing somebody prepares a state of a system, any one of the states of an orthonormal basis I. Behind your back, somebody creates a system in some state I, but doesn't tell you which state they've created it in. So it's definitely an electron or a spin or a composite system or whatever it happens to be. Has been created by somebody else in a particular state, but all they have told you is a probability distribution for what state they created the system in. Okay? In other words, what we can imagine is somebody creating an electron by putting it into a magnetic field, and that magnetic field could be up or it could be down. And they tell you, here's an electron. It's either up or down, but I'm not going to tell you which. And I'll give you a probability, though. 75% likelihood that it's up, 25% likelihood that it's down. This is not a situation where you would write up plus down, or even 3/4 up plus 1/4 down. That's not right, but you know what I mean. You wouldn't add the states together at all with a definite phase. You would just say you don't know what state it's in, and the system is described statistically with a greater degree of statistics than if it had been in than if you knew what state it was in. Even if you knew what state it was in, certain measurements would still be probabilistic. If you knew what state it was in, certain experiments might be definite and certain others might be probabilistic. But here's an added degree of probability, an added probability aspect to things, that not only if the system was in a definite state might you not know the answer to every question, but you might not even know what state the system is in. Under those circumstances, you use an object called the density matrix instead of state vectors. Density matrices are kind of a looser concept, a concept when you don't know what state the system is in, and it's a probability distribution for different states. All right. So let's suppose that somebody has prepared the system definitely in one of the basis states, I, with a probability, let's call it rho sub I. I'm using rho now instead of p, just because it's a standard convention for this situation to call it rho. So that's the rho then is the probability for the ith state. Now we can make a matrix out of rho. All right? We can make a matrix out of rho, and here's the way I'll make a matrix out of rho. I'm just going to, this is the matrix in the I basis, so this is I equals 1, I equals 2, I equals 3, I equals 4, likewise with the rows. It's going to be a diagonal matrix, and its entries are just going to be row 1, row 2, on the diagonal, row 1, row 2, row 3. All other elements 0. The rows are real numbers. They're positive numbers because they're probabilities, and they're all less than 1. And one more thing, and this is called, incidentally, this is called the density matrix. It's called rho, and it's called the density matrix. It's the analog in classical physics of the probability density, what we call P sub I. But it's now just been organized into a matrix with diagonal matrix elements. The elements are all real, and obviously they are the eigenvalues of this matrix, because whenever a matrix has been written in diagonal form, the diagonal elements are its eigenvalues. One more thing you can say, the trace of the density matrix is 1. Why is that? Because probabilities should add up to 1. Okay? So if the sum of all the probabilities adds up to 1, then the trace of the density matrix adds up to 1. Now, let's suppose we have some observable. Let's call the observable f. And it's also a Hermitian operator. Well, we have an observable f. It's a Hermitian operator, as always. Let me define now the average value of f. If we had an ordinary state, in other words, if we knew which state we were in with probability 1, then the average of f would just be the expectation value of f in that state. If we were in the ith state, the average of f would just be the expectation value of f. Okay, that's obvious, right? All right. I say more generally, when you have this uncertainty about which state you're in, that the right answer is that the average of f, I won't indicate it the same way. I won't indicate it by a bra and a ket, because it's implicit in that I have a particular state. I'll just write it as the average of f is equal to the trace of the product of f and rho. Let's see if we can make any sense out of that formula. That formula is quite similar to the corresponding classical formula, summation over I of f sub I times p sub I. Similar formula. Trace being replaced, or sum being replaced by trace, a classical function being replaced by an operator, and the probability distribution being replaced by the density matrix. Okay, it's called density matrix because it's like probability density, or probability, yeah. Okay, let's work out what this thing is. Let's work out what this thing is. The trace, we can pick any basis we like, but let's pick the basis in which rho is diagonal for simplicity. assuming that rho is diagonal in some basis, then this just becomes, the trace tells us, where's the definition of the trace? The trace tells us to take the basis, take the thing whose trace we're taking, f times rho, and close it up again, and sum over I. Okay. That's the trace of f times rho. Okay, now I'm going to do a trick which we talked about last time. We never really used very much, but I'm going to use it now. If we have a basis of states, then the unit operator can be represented as the sum over the states of the dyads made up out of the basis vectors. So let's, and what this means is you can always stick an expression like this between anything else and not change it. So in particular, I'm going to stick it between f and rho. All right, so that'll give us, now we have two sums to do, one for the definition of the trace, and one for resolving the identity. This is called resolving the identity by using a complete basis of states. So that would give us I, f, j, j rho I, summed not only over I, but also over j. Summed over I for the trace, summed over j to resolve the identity. Good. Now, rho, in the basis that I'm using, I'm assuming is diagonal. Right? That means that I has to equal j, otherwise we don't get an expression. All right. In that case, this just becomes the ijth matrix element, the diagonal matrix element of rho. I has to equal j. We'll get nothing unless I equals j. Right? This just becomes rho sub I, the ith entry into the matrix, and this becomes fii. Well, what is this? This is the expectation value of f in the state I. This is the probability that the state was made in configuration I. And this is just the sum of the expectation values of f weighted with the probability distribution for different states. Okay? So this makes sense to call this the average of f. But we see now a quantum mechanical version of this formula over here, in which, as I said, sum is replaced by trace, and probability distribution is replaced by rho. Here's a little theorem that you can prove. It takes 2 seconds to prove. If you have the product of two operators, A and B, the trace of A times B is the same as the trace of B times A. Work that out. Even if A and B don't commute. The trace of the product doesn't matter which way you order them. And so, in fact, it doesn't matter which way you order f and rho. Trace of f times rho is the average. Okay. That gives us the concept of a density matrix. Let's just look at some analogies with P. First of all, the sum of P sub I should equal 1. The analog is that the trace of rho is equal to 1. Trace of rho is equal to 1. So that's just another example of trace and sum being essentially the same thing. Good. Now I'm going to give you the concept, the quantum mechanical concept of entropy. This is the quantum mechanical entropy of a given density matrix. Now, first of all, the definition is such that if you know what state you're in, only one of these rows is 1 and all the others are 0, then the entropy is 0. For any quantum mechanical state, any real quantum mechanical state of the usual kind, the entropy is 0. The entropy is not 0, not because quantum mechanics has in it a built-in probabilistic aspect, but because you simply didn't know what state the system was made in. Right? You weren't told. That's the source of entropy in quantum mechanics, lack of knowledge about the state, not lack of knowledge even if you knew the state. Okay, the answer for the entropy, the definition of the entropy, given a density matrix rho, first of all, here's how you use it to calculate averages. But second of all, the definition of the density matrix, well, let's first write down the classical formula. The classical formula was sum on I minus of p sub I log p sub I. Well, the answer is trace minus the trace of the density matrix rho times the logarithm of the density matrix rho. What the hell is the logarithm of a matrix anyway? Well, there's a general answer to that, but let me give you the answer in the simple case where the matrix can be brought to diagonal form. If the matrix in some basis is diagonal, then the logarithm of the matrix is just the matrix made out of the logarithms of the eigenvalues. Log of rho, log rho 1, log rho 2, and so forth and so on. All right. So what is this? This is, of course, just the sum of the rho sub i's log rho sub i's, exactly as it is classically, but I've written it in a form now that's more appropriate for quantum mechanics as the trace of rho log rho, and so it has meaning in a vector space, not just as a classical probability distribution. This is the definition of the entropy. It has the property that if only one and only one of the rows are non-zero, in which case it has to be 1, because the trace of rho has to be 1. If one and only one of them is non-zero, then the entropy is 0. Okay? 1 times log of 1 is equal to 0. If the probability distribution is uniform, all states having equal probability, that would be the case where this would be proportional to the unit matrix, then the entropy here is logarithm of the number of states, logarithm of the dimensionality of the space of states. So if you know nothing about the system, you don't know how it was prepared or anything like that, then the entropy is just logarithm of the total number of states, which means the logarithm of the space of states, logarithm of the dimension of the space of states. And that's taken over practically directly from the classical concept of entropy, and it plays the same role. It's an indication of lack of knowledge of the system, knowledge that you could have, but that you don't have. In other words, the knowledge that is there to be gotten, but which you may have been too lazy to get. What's all of this have to do with entanglement? Well, I think we're going to have to quit now. Next time, I'm going to show you what this has to do with entanglement, but basically I'll just outline it for you. When you have a system which is composed of many parts, or let's say 2 parts to be specific, you may be interested in only one of the parts and not look at the other part. You may have a system which consists of 2 entangled parts. They may or may not be entangled. In particular, it's interesting when they are entangled, A and B. They're in some state which is an entangled state of the 2 systems, but you're only going to do experiments on A and ignore B altogether. Right? Then the question is, how do you describe A without reference to B? There must be some description that you can use for A, which contains all possible experimental information that you could do on A if you're never interested in also looking at B, if you don't look at B. And the answer is you use a density matrix to describe A. If A and B are entangled, then the density matrix will have entropy. If A and B are not entangled, it will not have entropy. So one diagnostic for looking at a system or at a composite system to find out if things are entangled is to determine what's called the entanglement entropy of the 2 systems. And it's a measure of how badly entangled they are. We'll come to it next time and we'll work it out. And we'll work out some examples. I want to work out some real examples to show you how entanglement entropy codes the fact that systems are entangled.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.